Welcome back to Chem 4300. In this video, we're going to continue Chapter 4 on rotational motion, and we're going to look at derivations of expressions for the rotational energy of rigid bodies, and also we're going to look at classification of molecules. So let's start with the expression for kinetic energy that everyone is familiar with, which is that kinetic energy is 1/2 mv squared. For a system of particles, it's going to be 1/2 and then the sum over all the particles, so m alpha and then v squared alpha. We're going to define the velocity vector here. We're going to define this whole problem actually in the principal axis system of the rigid body. And so the velocities are defined relative to the center of mass. So this kinetic energy will be purely rotational kinetic energy. And I'm going to take this v squared and I'm going to turn this into a dot product. And then what we're going to do is we're going to realize that the linear velocity vector is the cross product of the angular velocity vector with the position vector. So with this definition that we saw before, we're going to substitute it in there, and we're going to get this expression here. Now, I'm going to take the omega part out of this. I can do a little rearranging here, and since the omega doesn't depend on the alpha index, I can pull it out of the sum, and I can rearrange that to be of this form. Bringing that mass over next to the velocity vector, that becomes the linear momentum vector, and now we recognize this sum as the sum over all the individual particle angular momenta, which is the total angular momenta here. So now we can turn this part here into the j angular momentum vector, and the kinetic energy becomes 1/2 omega dot j. Okay, let's keep going with this though. What we also know is that j can be given by I dot omega, so we can remove the j from our expression and we can turn this expression into 1/2 omega dot I dot omega. So now we have the kinetic energy in terms of the moment of inertia tensor and the angular velocity vector. And this is very analogous then to what you might remember from the linear kinetic energy expression, so involving the linear velocity. So in other words, instead of mass, we have the moment of inertia tensor. Instead of linear velocity, now we have the angular velocity effectively squared there. Let's take this expression and let's rewrite it in the using the moment of inertia tensor in the principal axis system. So if we're in the principal axis system, the kinetic energy expression would look like this. And now omega A, omega B, and omega C would be the components of the angular velocity vector in the principal axis system. Now we also know that in the principal axis that the angular velocity vector A times the moment of inertia tensor component A is going to give us the angular momentum vector component JA. So the angular momentum vector, if I take this expression for the angular momentum vector component JA and I square this, then I have IA squared omega A squared. And if I divide that by IA, then I have that expression there. So I can do the same thing here and I can do the same thing here. So I can take this definition of the angular momentum vector components written in the principal axis system in terms of the principal axis values of the moment of inertia tensor and the angular velocity vector components, and I can rewrite this expression into this expression here. And this is the general expression that we're going to be using for the rest of the course for the kinetic energy, the rotational kinetic energy of a rigid body. Now let's move on to looking at different classifications of rigid bodies based on the values of their principal components of the moment of inertia tensor. So the most symmetric rigid body is a rigid body that has IA equal to IB equals to IC. This is given the name spherical. So this has we classify any molecule where IA and B and C are equal as a spherical molecule. And these are molecules that have 2 or more threefold or higher rotational symmetry axes. So if you see those symmetries in a molecule, 2 or more threefold, then you know you have a spherical molecule. So an example of that would be something like methane. Now there's also a class of molecules called the symmetric molecules, which has one threefold or higher symmetry axis in the molecule. And in those cases, then two of the components will be equal, and we're going to separate these into two different subtypes of symmetric. So there's going to be what's called the prolate symmetric and the oblate symmetric. In the case of prolate symmetric, B and C will be equal, and A, the smallest one, will be unique. In the case of oblate symmetric, A and B will be equal, and the largest component, C, will be the unique one. So we're going to define, in the case of prolate, C is going to be called I perpendicular, and B and C will be called I perpendicular, and A, the unique one, will be called I parallel. Whereas in the oblate case, A and B are going to be called I perpendicular, and the C unique one is going to be called I parallel. Examples of these two cases are methyl fluoride or CHF3. And now the other cases would be, example, asymmetric case would be like the case where we have absolutely these guys are all dissimilar from each other. And so you can have molecules can have some symmetry axes, but if they're not threefold or higher, then you can be in the asymmetric case. So for example, CH2Cl2 has a twofold symmetry axis, but that's not enough to move it into these higher symmetry classifications. And then finally, the last case we'll be looking at here is the linear case, where all the atoms are on a line, so like carbon dioxide or OCS. And in that case, one of the components, the A component, is going to be equal to 0, and the other two components are going to be equal to each other. So let's look at each of these cases in more detail in terms of their kinetic energy expressions. So the spherical case, which the example is methane molecule, is here. And if we took a methane molecule with typical bond lengths, we would get a value about on the order of this size here, so 5.3 times 10 to the minus 4 grams centimeters squared. And as I said before, spherical molecules have more than one threefold symmetry axis, which you can see in this drawing here. Now, there are other examples of spherical cases, like besides the tetrahedral, there's also octahedral, and I'll leave it as an exercise for you guys to work out, what the moment of inertia component, the IA, IB, and IC all being equal to I in this case here. For the kinetic energy, then, we can write down our expression where all the A, B, and C are equal, so we can just bring them all down in the denominator as 2I, and this top part, which is JA squared plus JB squared plus JC squared, we recognize is just the length of the angular momentum vector squared, so that just becomes J squared over 2I. So that's a very simple expression for the kinetic energy in the spherical case. Now, for the class of molecules that are symmetric, the ones that have a threefold or higher symmetry axis, but not more than one threefold, then we're going to be looking at these cases where two of the principal moments of inertia tensor, principal components of the moment of inertia tensor are going to be equal, and one of them will be unequal to the other. So that one that's unique is going to be called the figure axis of the symmetric molecule. So in the case of prolate, the figure axis will be the smallest principal component. That will be the unique one. In the case of oblate, the figure axis will be associated with the largest principal moment of inertia. So in the prolate example, where A is smaller than B and C, which are equal to each other, then we're going to label the two equal as I perpendicular, and A, which is the unique one, is I parallel. And an example of that would be fluoromethane. And here you see the drawing of the molecule, and this is the direction of the A principal component axis. And here are the values that you would calculate using typical bond lengths for this molecule. And looking at the kinetic energy, then we would write down now that the JA is over 2I parallel, or which would have been IA. And then for JB and JC, now they're over the common I perpendicular, which we'll write here. We can take this expression and we can rearrange it so that it's in terms of the total angular momentum vector length, J squared, and then in terms of just one of the components, which is the unique axis, A, so we can write down the JA component squared too. So we can write this in terms of the total length squared of the angular momentum, and then the one component, the JA squared, the figure axis component for the angular momentum vector. Now contrast that to the oblate case, and this case we're looking at a molecule like trifluoromethane, and here the C-axis is along the CH bond, and we have the case where A and B are equal to each other, so those are defined as perpendicular, and C is the unique figure axis, which is defined as I parallel. And for typical bond lengths, these are the values you would get for trifluoromethane, And for the kinetic energy, then we have a slightly different version. Now we have JA and JB, which share the common moment of inertia component. So now we have 2I perpendicular below. And for JC, the figure axis, we have JC squared over 2I parallel, which we can rearrange this guy also in terms of just J squared, the total length of the angular momentum vector, squared, and then the JC component squared over here. So contrast that with the prolate case where we had JA over here. So in the previous slide, we had this expression for the kinetic energy with the prolate, with JA as the figure axis component, and over here JC is the figure axis component. And I give you some more other examples of geometries that are symmetric molecules and some derivations, the results of those derivations for their components. I'll leave this for you guys to check on your own. And in the asymmetric case, where A, B, and C are unequal to each other, then a simple example would be something like dichloromethane, and here are the components you would calculate for typical bond lengths. The asymmetric molecule, you can see in this case it has a twofold axis in planes of symmetry, but doesn't have the threefold or higher, so that means that it's not going to move into the symmetric case, so it's going to stay in the asymmetric category. And for the energy then, because all of these guys are different, then we go back to our original expression that we derived at the beginning of this lecture. And then the last case we're going to consider is the special case of a linear molecule where one of the components, the A component, is 0, the smallest one is all the way to 0, and B and C are equal to each other. And so now we have, say, two different examples of the OCS or carbon dioxide. The A axis is along the long axis, including the line of atoms, and these are the values that you would get. So the IA is always 0 in these cases, and IB and C are equal to each other. Now, here are some other sort of configurations where you can calculate the moment of inertia component. And then finally, for the kinetic energy of this case, it's a little bit tricky. We have to be careful here. Because IA is equal to 0, that means that there can be no rotational motion about the line of atoms, which is defined along the A axis. So all the rotation has to occur perpendicular to A. So that means that for this case, we started out generically writing down the kinetic energy like this, but we know that IA, and as a result, omega A is going to be 0, so we write the kinetic energy in this form. And of course, omega B squared plus omega C squared is the length of the angular velocity vector. And so this becomes K is equal to 1/2 omega squared I in this case. And since similarly we can do like we did before, we can use our definition of the angular momentum in terms of the principal components and the angular velocity vectors. We can write that in this case to be I squared omega squared, so we can rewrite this guy as K is equal to J squared over 2I, and that's the kinetic energy of the linear rigid rotor. Now it looks identical to the spherical case, but be careful, this is not the same because this case was derived with the IA component of the moment of inertia tensor being 0. Okay, so that's it for this video. In the next video, we'll look at how you can diagonalize a moment of inertia tensor.